Good evening and welcome everyone to the third weekly interactive sessions of this NPTEL Gate platform. So today we'll be looking at some problems in plastic analysis and partial differential equations. I'm Naresh. I'm a research scholar at the Department of Civil Engineering at IISc. So we have had two sessions before this. The first one was on engineering mechanics, the force systems, equilibrium, and so on. The second one, we had a session on friction and the plastic analysis of structures. So this is the third in the series. Here we'll continue with the problems on plastic analysis, which appeared in previous year GATE papers. And we'll also look at the methods to solve partial differential equations. If time permits, we'll also be solving problems today, or else we'll take it forward in the next session. So for the benefit of those who might be watching this video offline or watching the recording, I can say this ahead again. You can log into this groups.google.com, and in order to access the recordings and the materials that I'll be presenting in these sessions, you can log into this groups.google.com and you select all groups and messages and search for this NPTEL Gate CE 2023, and you can just enter. So that will take you to this one, which is the group created by me. You can join this for posting your queries, accessing the content, and also you can give suggestions for the next sessions. So I hope that is helpful. So let us get started. Let's start with a recap of what we looked at in the last week. So we looked at problems involving friction and its applications. So we solved one problem on that. Then we looked at plastic analysis of structures. So what is the need for plastic analysis of structures? We saw that there is always reserve strength beyond the yield strength, beyond the yield limit. So we saw structures have strength beyond the yield after yielding, and also it simplifies the analysis of indeterminate structures. And there are various concepts involved in plastic analysis. We saw that if a structure or a beam, for simplicity, we take a beam, subject it to some loading, let us assume a mid-span concentrated force, and we keep increasing the load P from 0 to a certain limit until the beam collapses. So we saw that as the load is increased, initially there is a linear elastic response. At some point, the extreme, suppose this beam has a cross section like this, right? If the beam has got a rectangular cross section like this, at a certain load P, let us call it P yield, Py. At this load, the force is so high that the stress in the cross section remains linear, but the extreme fibers, the stress in the extreme fibers of the cross section have reached the yield stress of the material. What happens beyond that point? Beyond that point, the load can further be increased, but the cross section, the stress in the extreme fibers cannot exceed Fy. So what happens is the fibers next, the other fibers in the cross section, they start reaching the stress Fy. So the stress distribution in the beam cross section is no longer linear. You get a bilinear stress distribution like this. So up to a certain limit, we have the yields. A part of the section is yielded, and the remaining part of the section remains elastic, linearly elastic. So at this stage, the stiffness of the beam is coming only from the linear elastic portion. After the fibers have yielded here, that has no stiffness. So as you know, the material curve of elastic, perfectly plastic material is something like this. So there is a linear elastic response followed by a perfectly plastic response. So here the stiffness is 0, which means these regions of the beam do not contribute to the elastic stiffness. So the stiffness of the beam is reduced significantly and the curve becomes nonlinear. As the load is increased further, this region of plastically strained region increases until it reaches the neutral axis. So at this point, the entire cross section is plastic. It is no longer elastic. So at this point, the beam becomes completely. So at this point, the cross section is completely yielded. It has got no stiffness. Therefore, the beam collapses. So this is the plastic. For this beam, for the simply supported beam, the load at which the middle cross section becomes completely plastic is called the plastic collapse load, because once this is fully plastic, it supports a moment which is given by this. So there is a stress, there is a constant stress above and below the neutral axis. So this will you take an infinitesimal element and you integrate the force due to this multiplied by the distance, you get some moment. So the moment at which this happens is called the plastic moment capacity of the beam, MP. And once the plastic moment capacity of the beam has been reached, it has got no more stiffness. So it forms what is called a plastic hinge. It is free to rotate, but at a constant moment of MP. So this we have seen in the last week. If you haven't attended the last week, you can go and look at the YouTube link of the previous lectures. So you can look at it. So this is the mechanism by which a beam collapses. So as the load is increased from 0 to of what is called a plastic hinge. And what is a plastic hinge? Plastic hinge is formed when the entire section is yielded plastically. So basically, this is what you need to remember for this session. And once plastic hinges are formed in a structure, it becomes a mechanism. So we saw what is the difference between a structure and a mechanism. A mechanism is something that cannot take any load. It cannot take any load. A mechanism just accelerates. So we saw that if we have a truss structure like this, subjected to some force, it raises the applied load by generating internal forces arising from the deformation. On the other hand, if you remove the middle member and you have something like this, both are pin connected, all joints are pin connected, and you apply a load like this, it collapses this way. It forms a 4-bar mechanism. So here it does, the members don't deform, they don't generate any internal forces. They accelerate, they just rigidly rotate and translate, and they accelerate, they cannot take any load. So at the verge of collapse, what happens is there are sufficient number of plastic hinges formed and the structure becomes a mechanism. It is close to becoming a mechanism. So a structure cannot take any further increase in the applied load. So that is the point, we call it as a collapse load. So we have seen what are plastic hinges, and we saw what are the 3 fundamental conditions that needs to be satisfied by a structure at the point of collapse. So when a structure is here, at the verge of collapse, what happens? First condition is it becomes a mechanism. There are sufficiently many plastic hinges formed such that it becomes a mechanism. The second condition is it is still in equilibrium with the applied loads. So the internal forces in the structure are in equilibrium with the applied external forces and the reactions. And the third condition we saw is it obeys yield condition. That the moment in the structure at any point is always less than or equal to the plastic moment capacity, because there is the moment capacity. The moment cannot exceed it under our assumptions of perfectly plastic material. So we saw that if all these 3 conditions are satisfied, we get what is called the plastic collapse load, PPL. If not, we have theorems to estimate the plastic collapse load, PPL. So we saw one theorem, which is the static theorem. So what does the static theorem say? If you obey conditions 2 and 3, that is, you have an arbitrary bending moment diagram, which is in equilibrium with the applied loads and also satisfies the yield condition, M less than or equal to MP. If these 2 conditions are satisfied, we get an estimate of the collapse load PS, which is always less than or equal to the true plastic collapse load PPL. And what was the second theorem? The second theorem stated that if we assume an arbitrary mechanism, so this is called the kinematic approach. If you assume an arbitrary mechanism, what is a mechanism? So for this beam, this is called a mechanism. So the formation of plastic hinge in the middle converts this structure into a mechanism for the simply supported. So once it has formed a mechanism, the moment in the plastic hinge is equal to NP. So we assume such a mechanism has already formed and enforce equilibrium to determine the force at which the mechanism forms. That gives an estimate of the plastic collapse load called P kinematic. And P kinematic is always an upper bound to the true plastic collapse load PPL. And the third one is if all three conditions are satisfied. So in the first case, we are satisfying conditions 2 and 3. The second case, for the kinematic approach, we satisfy conditions 1 and 2. And in the third case, we satisfy all the three. So 1 and 2, satisfying 1 and 2 gives an upper bound, satisfying 2 and 3 gives a lower bound, and satisfying all the three gives exactly the plastic collapse load. And for solving problems, we saw the concept of principle of virtual mode. So don't worry too much about this. Problem solving is actually easy, plastic analysis. The concepts are a bit involved, but don't worry about the theorems. It will be very easy while we solve problems. So are there any questions from the last class? You can take if there are any questions from the last class. Or if you have any questions based on what I just discussed, you can take them up. No questions? Okay, let me proceed. So here are the steps to solve a problem by the kinematic approach, right? Usually in GATE, they don't ask questions involving the static approach because for statically indeterminate structures, you need to get a bending moment diagram which is in equilibrium, and that is difficult. So in as I said in GATE 2014, 2022, 2008, we have had 14 both sessions, set 1 and set 2. We have had questions from the plastic analysis of structures. And all of them require us to use the kinematic approach. So here are the steps to solve for the collapse load of a structure by the kinematic approach. So the first step is to draw the qualitative bending moment diagram. So in case you haven't attended the last class, you may find it a bit difficult to understand this, but I'll explain, no problem. As we solve problems, I'll explain. If suppose in the last class we solved this problem of propped cantilever beam. So we had this problem of a propped cantilever beam. This was, I think, 2014 set A question. Subjected to a mid-span concentrated force of magnitude P. So we were asked, and it was given that the plastic moment capacity of this beam is MP, and we are asked to find the collapse load of this beam by kinematic approach. What is the collapse load of this beam, of this structure? Given the plastic moment capacity of this beam is MP at every section, what is the collapse load? So how do we solve it? So we are using the kinematic approach. So we need to find where the plastic hinges will be formed. For, as I said in the example that we were discussing, for the simply supported beam, the maximum bending moment occurs in the middle. So compared to anywhere else in the structure, the stresses will be highest in the middle section. So I said a plastic hinge will be formed in the middle. For this structure, we need to find where the plastic hinges will be formed. For that, what guides us is the qualitative bending moment diagram. So by qualitative, I mean you don't need to get the exact numbers in the bending moment diagram. So if you get the exact numbers, that is the analysis, that is the elastic analysis, right? But you don't need to get the exact numbers. So let us look at the qualitative bending moment diagram, just the shape of the bending moment diagram, just to see where the maximum moment occurs. So it is very simple. At the right end, it is the hinge. So here the bending moment has to be 0. And this reaction force acts upwards. So as we go away from the support, you generate a sagging bending moment, which is positive. Right below the point load, you will have a maximum bending moment. And this support is a fixed support, so there will be some negative bending moment or hogging bending moment at this end. So this is the qualitative bending moment diagram. We don't know whether this value is higher or this value is higher or what those values are. But we know a maximum bending moment can either occur here or here. So we have drawn the qualitative bending moment diagram. That is the first step. So the first step is to draw the qualitative bending moment diagram that we have done. The second step is to mark plastic hinges at the absolute maximum of the bending moment diagram. So as I said, the moment is always in the elastic range. It is highest here or here. So as we increase the load, the maximum stresses will be reached at this section or this section. And once the stresses increase so much that the entire cross section becomes plastic, then it forms a plastic hinge. So it is most likely to form plastic hinges either here or here. So these are the two locations. Why not anywhere else? Because if it has to form a plastic hinge anywhere else, it should have already formed a plastic hinge here because the stresses are higher here than anywhere else in the beam. So the stresses are higher in these two locations compared to anywhere else in the beam. So first plastic hinge will be formed here. And once it forms a mechanism, it cannot increase the stress beyond that point. So once it forms a mechanism, the structure will just collapse. So that is the idea. Once plastic hinges are formed and the plastic hinge is such that it forms a mechanism, the stress cannot increase any further in the structure because it has started accelerating. It will not generate any internal force. So the second step is also done. What is the second step? Mark the plastic hinges at the absolute maxima. Fine. Now, how many mechanisms are possible? So if you have attended the last class, you will know that the number of mechanisms, suppose n is the number of possible mechanisms. It is related to the number of plastic hinges as, suppose h is the number of plastic hinges. Actually, it's number of independent mechanisms. I'll say why it is important. And you have, suppose S is the degree of static indeterminacy. Then these three are related by the formula. The number of possible independent mechanisms is H minus S, right? Why is that so? For example, it is easy to see in this example, for this to form a mechanism, you need only one plastic hinge to be formed. Right, and the mechanism is like this. Once this section becomes fully yielded, it cannot resist any moment and it forms a plastic hinge like this. It cannot take any force. But here, is it enough to form a plastic hinge in the middle? No, because even if it forms a plastic hinge in the middle, it is not going to accelerate. This is still attached. So this will flex as a cantilever beam and this will carry some load. So this is not enough. This is still a statically determinate structure. So one more internal hinge has to be introduced to make it a mechanism. So that hinge, if it happens anywhere here, then it forms a mechanism. So you know that the statically determinate member has exactly number forces which are needed to keep it stable. And if you remove one of the member forces, then it becomes unstable. So that is exactly what we want. We want it to become a mechanism. So the number of mechanisms possible is the number of plastic hinges minus, or the number of hinges required is nothing but the number of mechanisms plus the static indeterminacy. So the number of independent mechanisms is H minus S. In this case, what is the mechanism? We have identified two plastic hinges. So at the verge of collapse, the structure will go to some shape like this. And once it forms a mechanism, what is the moment capacity, or the moment at these plastic hinges? It is the moment capacity. Here we have a hogging moment, so I'm marking it in the same direction. It is MP. Here we have sagging moment, so I'm marking it in this direction, which is MP. So that is done. We have obtained the number of mechanisms Here in this case, there is only one mechanism, which is this. So this is mechanism 1. And what else we should do? We have to determine the relationship between the applied load and the moment capacity NP. Suppose the load P is acting here. For this, how do we obtain this? Yes. So how do we obtain the plastic collapse load? The relationship between the load at the collapse and the plastic moment capacity. We have two methods. One is the principle of virtual work, which we discussed last time, or the equilibrium of parts. So this I didn't discuss last time because principle of virtual work is much easier compared to, it takes less time than equilibrium of parts. So for this problem, this is the deformed shape. At the verge of collapse, this is how the structure will look like. And what does the principle of virtual work state? Principle of virtual work states that the work done by the internal forces is equal to the work done by the external forces in moving through any admissible virtual displacement. Right? So in this case, this is the structure at the verge of collapse. So suppose this beam has rotated by some theta and is mid-span. So this is an isosceles triangle. So this will also be theta. And if you use the exterior angle theorem, this will be theta plus theta. So this is a triangle, and using the exterior angle theorem, this will be 2 theta. Now, if you see the external work done, and suppose the midspan comes down by a distance delta. What is the work done by the external force P? It is P into delta. And in this case, delta is equal to theta times L by 2. Theta times L by 2. So it is P theta L by 2. And what is the internal work done? Internal work done is you have a moment, internal moment N, which is rotating this beam through an angle theta. So that is NP into theta plus, here you have a moment MP, which is rotating this segment of the beam. Suppose there had been no plastic hinge, this beam segment would have been straight. The straight beam had to rotate by 2 theta to make it to the current shape. So if the plastic hinge has formed and the structure is collapsing, in the process, if it rotates this way, this end by theta, and the middle road comes down by delta, then this segment of the beam has undergone a rotation 2 theta. So this plastic hinge has done the work done in the plastic hinge is MP times 2 theta. So this is nothing but 3 MP theta. Equating both, you will get P is equal to 6 MP by L. So this was the problem that we solved in the last session. So this is using the principle of virtual work, but instead of using the principle of virtual work, you can also use the equilibrium of parts. So I'll demonstrate it in today's problem. So this is a problem that appeared in GATE 2014 second set. In this case, we have an overhanging beam. So we have an overhanging beam of span one span. So one span is L and the other span is L by 3. So this span, there is a midspan concentrated force of magnitude P. Here you have an end span concentrated force of magnitude P by 2. So let us go step by step. What is the qualitative bending moment diagram of this? So, at this end, you will have 0 moment because it is a free end. Right above the intermediate support, you will have a hogging moment because this force is acting downwards. So you'll have a hogging moment right here. And right below this, so there will be an upward reaction here. And right below the concentrated force, you'll have a sagging moment. You'll have a sagging moment. And this end is hinged, so you will have 0 moment there. So this is the qualitative bending moment diagram of this beam. So for this plastic hinge on this beam can either happen here or here. Cannot happen anywhere else. Before that, the structure would have collapsed. So plastic hinge can form here or here. Fine. So let us draw the deformed at the verge of collapse. The structure will look something like this. So before that, so let me put only the supports. Now, how many plastic hinges are there? There are two possible locations of plastic hinges. What is the degree of static indeterminacy of the structure? Anyone? Simple, right? What is the static indeterminacy of the structure? Yes. It is statically determinate, right? So the static indeterminacy of the structure is 0. You can see because it is just got right. You have three equilibrium equations and you have three unknown reactions, 1, 2, and 3. So statically determinate. So the static indeterminacy is 0. And what is the number of mechanisms that are possible? It is H minus S. There are two possible mechanisms. What are they? In one case, the plastic hinge is formed here. And in the other case, plastic hinge can be formed here. So this is mechanism 1. And this is mechanism 2. So how does the beam deform in the mechanism 1? This portion is remains straight. So this is how it deforms. And mechanism 2, this is how it deforms. And let me indicate the applied forces. Here we have an applied force of magnitude P, here P by 2. Same in this case too, P and P by 2. Now let us analyze the mechanism 1. So in mechanism 1, we have something like this. This is L by 2. This is L by 2. This is L by 3. And the applied forces are P by 2. And this is the only hinge. Suppose the rotation here is, suppose the rotation here is theta. What is the rotation here? It's an isosceles triangle. So this is also theta. What is the rotation of the beam segment here? By exterior angle theorem, this is 2 theta. What is the rotation here? They are intersecting angles. So opposite sides of intersecting lines. So this is also theta. And suppose this is delta. The midspan deflection of this is delta 1. Let this be delta 2. Let us write down the work done by the external forces. The work done by the external forces in this case is P is moving through delta plus this P by 2 is moving through delta 2, but these two are in opposite directions. The load acts downwards and the displacement is upwards. So the work done is negative. So minus P by 2 times delta 2. What is delta 1 from the geometry? Delta 1 is L by 2 times theta. And delta 2 is, this is theta and this is L by 3. This is L by 3 times theta. So the external work done is P L theta by 2 minus, you have 1 by 2 multiplied by 1 by 3. So P by 6 L theta. So the external work done is nothing but, so this is 1 by 2 minus 1 by 6, which is PL theta by 3. So that is the external work done. What is the internal work done? So the internal work done. How many plastic hinges have been formed? There's only one plastic hinge. There is no moment here. This is a free hinge. Sorry, this is a hinged support. Here there is no moment because the beam remains straight. This is a free end. So the only plastic hinge is formed here. And it is sagging and the moment capacity is MP. Note that the beam has rotated in the direction of MP. So the work done is MP times 2 theta. Equating both, we get MP into 2 theta is equal to PL by 3 into theta. So this should hold for arbitrary theta. That is what the theorem of principle of virtual work states. So it should hold for arbitrary kinematically admissible virtual displacements. So kinematically admissible means we respect the support conditions. The assumed displacement obeys the support conditions, and we have ensured that we have made sure that the displacements are zero at the supports and the rotations are allowed. So that obeys the support conditions. So so this theta is admissible. So this should hold for theta not equal to 0, which means the collapse load is 6 MT by L. For this mechanism, we also have another mechanism and we need to look at it also. So which is the actual collapse load? So we'll come to it. So in case the middle one, in case the plastic hinge is formed here, it will collapse at a load of 6 MT by L. Alternatively, if the plastic hinge had formed here, we'll see at what load it will collapse. So this is mechanism 2. You have the beam like this. This portion remains straight and there's a plastic hinge formed here. So this will support a moment of MP and this has rotated by theta. And we have the applied force P by 2 here. So what is the external work then? The work done by the external forces is P by 2 times this delta. So what is delta? In this case, this is L by 3. This L by 3 times theta. So this is nothing but PL theta by 6. And what is this is not doing any work. Note that this P is not doing any work. This portion will not deflect significantly under plastic deformation. So it is P multiplied by 0, which is 0. So this will not contribute to the work done by external forces. And what is the work done in the plastic hinge? So this plastic hinge has a moment MP, which is making it rotate by theta. So the work done by that is MP into theta. Equating these two, we get P is equal to MP, 6 MP by L again. So in this problem, we got both of them to be equal. But suppose you get P1 and P2, the actual collapse is minimum of P1 and P2. So if you have, so in this problem, this is P2, P corresponding to mechanism 2. This is P corresponding to mechanism 1. In this problem, both turned out to be equal. But if they are not equal, you need to take the minimum of the two. Why? Because the kinematic approach gives an upper bound. It says which is higher. The collapse load we get is an upper estimate. It means that you have two estimates for the collapse load. Sorry. And both, one of them is above and one of them is close to it. So the collapse, as we increase the load, the collapse would have already occurred at the lower estimate. So it cannot go to the higher estimate. So out of the two, you need to select the smaller one. And in this problem, it is 6 MP by L, which is option C. As I said, you can also approach this problem by equilibrium of parts. Let me show it for in this case. OK, so or rather, we can also take it later. So this is another problem which appeared in 2008. So this is a 3-span continuous beam with mid-span concentrated forces in the second and third spans. How do we approach this problem? Same thing. Let us get a qualitative bending moment diagram of this. What does it look like? So let us start from the right hand side. So there will be an upward reaction here. So right below the concentrated force, let me draw it here so that I can correlate with the given figure. So right below the concentrated force, there will be a positive moment, a sagging moment. This is an intermediate support, so the beam will be bending like this. So there will be a hogging moment here, minus. Again, below the concentrated force, we have a sagging moment. Again, below this support, you have a hogging moment. And this is a load-free span, and there's only a hinge support at the end. So at this end, it has to have 0. So this is the qualitative bending moment diagram for this beam. So as I said, we don't know these magnitudes, but we know if at all a plastic hinge is formed, the possible locations are here, corresponding to this peak, or here, or here, or it can also be here. So the number of possible plastic hinges in this problem is 4. And what is the degree of static indeterminacy for this problem? Could anybody tell? Yes, it is simple, right? It is just 3-span continuous beam. You're able to hear me? Is that okay? Could anyone confirm? Is it audible? Okay, fine. Thank you. Okay, so this the static indeterminacy of this problem is just 2. You have got, just consider the vertical forces. You have got 1, 2, 3, and 4 vertical unknown forces. But you have only 2 equations of equilibrium, which is the moment and sigma Fy equal to 0. So the static indeterminacy of this problem is 2. So what are the number of independent mechanisms possible for this problem? It is H minus S, which is 2. Now let us draw the mechanisms. So when this structure is at the verge of collapse, what are the possible ways it can? So one way, mechanism 1, is like this. One way is it can form a plastic hinge in these 3 locations, and it can collapse like this. The other mechanism, the other independent mechanism is it can form a plastic hinge here and here. So these are 2 independent mechanisms. You can have many more. Say, for example, if you consider this, and this hinge, that also looks like a mechanism, but it is not. The reason is this beam is rigid. It will not allow any rotation about this point. So if suppose you say M3 exists and you draw a mechanism like this, this is not an independent mechanism, right? Because it will again give rise to the same. So because this portion, this beam is supported sufficiently, this is stable. Under an applied force, this cannot go down. This cannot freely rotate. So it again corresponds to this mechanism only. So therefore, it is not an independent mechanism. That is why I said the formula n equal to h minus r gives the number of possible independent mechanism. So as you can see, the one that I have drawn as M3 and M2 will give exactly the same internal virtual work and the external virtual work. So that is useless. So these 2 are the useful mechanisms. We'll analyze only these 2. Okay. So let us draw the deformed shape when the structure is about to collapse. How does it deform in the first case? In mechanism 1, structure will deform like this. So let us displace this point, and there is an applied force of P and P here in both cases. So there's a plastic hinge here, there's a plastic hinge here, there's a plastic hinge here, and there are supports here. So this P has displaced it by, say, some delta. And this is an isosceles triangle as in other cases. So what is this angle? It is 2 theta. What is the external work done? The first case, it is P multiplied by delta, which is theta times L by 2. And what about this P? The P is still acting here, but there is no mechanism here. It is a simply supported. This span is just simply supported. So it doesn't do any plastic work. It has some elastic contribution, but we are interested only in the work done by plastic deformation at collapse. So that is, it does 0 work. P multiplied by 0 displacement is 0. So we can add a plus 0. And what is the work done by the internal forces? The internal forces, if you mark, so there has been a plastic hinge formation here. So this is under a hogging moment of magnitude MP. Here there's a plastic hinge, so this is under a sagging moment of magnitude MP. Here there's a hogging moment of magnitude p. So the internal virtual work is mp times theta plus this np has rotated the beam by 2 theta, and this np has rotated the beam by theta. So the total work done is 4 mp theta. What is the next step? Equate the two. If you equate the two, you get an estimate of the collapse load as 8 mp by L. Is that the answer? No, because we have seen only one of the mechanisms. Let us call it the collapse load obtained by mechanism 1, PC1. Let us look at the next mechanism now. What is the next mechanism? We have, this is how is it? There's a plastic hinge formed here. And there's a plastic hinge formed here. This is already a hinge. So subjected to this applied forces, this goes down like this. This cannot go down because it is supported here. This can only deform like this. Sorry. This can only deform like this. And that deformation is elastic, which is much smaller compared to the plastic deformation. Right? So suppose this is the virtual displacement we are considering. This rotates by theta. This rotates by theta. And what about this angle? As in all other cases, this is 2 theta. So if a plastic hinge has formed here, we know that there will be resisting a moment, hogging moment MP here. Here there is no moment because it is already a hinged end, and here there will be sagging moment of magnitude MP. So what is the external virtual work done? The external virtual work, W external. This doesn't do any work because there is no plastic displacement here, and this does the work of P times delta, which is P theta L by 2. Delta is nothing but theta multiplied by L by 2. Is L by 2. L by 2 multiplied by theta. And what is the internal virtual work? So this plastic hinge, the rotation of this plastic hinge is happening at mp times theta. And the rotation of this plastic hinge results in a work done by this force mp on 2 theta. So this is 3 mp times theta. And the external virtual work done is p theta L by 2. Equating these two, theta theta gets cancelled as in other cases, and we get the collapse load of this beam subjected to mechanism 2. So this is mechanism 2, right? Is given by 6 mp by L. Equating the two above. So this is how we solve it. Now you see that there are two different magnitudes we got. So as if we assume collapse mechanism 1, we get a collapse load of 8 mp by L. And if we assume the collapse mechanism 2, we get a collapse load of 6 mp by L. Now which of these we should consider? We should take the minimum because the structure would have already collapsed when P2C is reached, because P2C is smaller than P1C. So structure would have already collapsed at this point. So it makes no sense to increase the load beyond P2C. Therefore, the collapse load of this structure is minimum of 6 mp by L and 8 mp by L, which is nothing but 6 mp by L. So which option does it correspond to? It is option B. Any doubts? I'll pause here for a few minutes. Do you have any doubts? Is everything clear? Okay, thank you, David. So please feel free to interact. You can, we're only a few in number, right? So you can interrupt me whenever you have a doubt or you have a problem. You can ask doubts. You don't need to wait for me to pause it. Okay, so I feel this is meant for interaction. These sessions are just meant for interaction. You can ask any number of doubts, right? Can be anything. So I'm ready to explain it repeatedly also. Mm. So don't worry about it. So in these problems, in the problem that we saw in the last week, and also in the problems that the two problems we solved today, the key thing is MP is given as some value. But how do we actually determine MP? So that we'll see in this problem, right? Given a cross section of the beam and the properties such as the cross-sectional properties and the material, right? Given all these details, how do we actually find out the plastic moment capacity of the section? So this was Alvin Gate 2022. So we are given a diamond shape, kind of diamond shaped section. So it's a square placed diagonally, square placed along its diagonal, and the diagonal is the bending axis. The ZZ axis coincides with a diagonal of the square. We are asked to determine the shape factor about this axis and the plastic moment capacity of this beam. So how do we approach this problem? Yes. Any feel free to put in your ideas. So we are asked to determine the plastic moment capacity of this beam. How can we? How do you approach this problem? So this has got nothing to do with plastic analysis. All these are valid for structures. Given a capacity, what load the structure can take, that is what we saw all this time. But how do we find the capacity itself? That we are going to see now. So let us start with what happens in a plastic hinge, right? We have a section. Sorry, this is bad. So you have a section like this. And this is the bending axis. And this is some other axis. This section is symmetric about both. When a plastic hinge forms, if you remember, I said all the fibers in the section have reached the yield stress. So the section is entirely yielded. So above the bending axis, we have compression, and below the bending axis, you have tension. And in this case, the sigma, the magnitude of sigma in both cases is equal to the yield stress. That is when a plastic hinge forms, right? So initially, as I said, initially there's a linear response. As the load is increased beyond the yield stress, some portion will become plastically yielded. And as the load is increased even further, the entire section becomes yielded. It takes this rectangular shape because the stress cannot exceed the yield stress of the material. So this is the ultimate state of the cross section when a plastic hinge has formed. So that is fine. That is so. Let us get started. So here, this dimensions are A, and this is a square. So what is this dimension? It is √2 times A. That you can just get by Pythagoras theorem. Now we are asked to determine the plastic moment capacity MP. So let me also draw the linear elastic range, right? So when the extremities of the cross section have just yielded, we have a distribution like this. Here we have Fy, and here we have Fy. So these are two cases. In this case, the moment in the section will be the plastic moment capacity MP. And in the second case, the moment in the section will be the yield moment My. So So how do we find the moment in the cross section? You know, from the beam theory, it is nothing but integral y df over the entire section. So because of this stress, there will be a compressive force. If you take a small element of the cross section, over that element, you will have a compressive force df. So what is df? df is nothing but sigma times dA. It is nothing but the force sigma times dA. And what is dA? It is just dx dy that you know from basic mathematics. So sigma, that's y here. Y sigma dx dy. What is the so in the case of plastic movement MP, the entire section has yielded. So the limits. So you have a double integration going from, let us say, over this region. This region is S, Y. What is sigma in the case of MP? It has yielded fully everywhere, independent of where the location is. It is Fy. Let me take it as dz dy. Now let us find out the limits of integration. So what are the limits of y? Y goes from minus. So this is root 2a. So vertical is root 2a. So this distance is a by root 2. Again, Pythagoras theorem, it goes from minus a by root 2 to a by root 2. These are the limits for y. And what are the limits for z? Z goes from, suppose at a height y, the strip is of width b of y. So z goes from minus b of y by 2 to b of y by 2. And we have y fy dz dy. So let us simplify this further. What is b of y? So the width at a height y, right? This strip is taken at a height y, and at a height y, the width of this section is b of y. What is b of y at? So we know that it is linear. So b of y equal to 0 is what? It is a by root 2. And b of y equal to a by root 2, what it is? It is 0. Sorry, at y is equal to 0, it is not a by root 2, it is root 2a. It is root 2a. And when it is at the top, when y is equal to a by root 2, it is 0. The width is 0. So what is b of y? It is nothing but root 2a minus 2 times y. Just substitute. If you substitute, it is a linearly varying function. So if you substitute y is equal to a by root 2, you see this goes to 0. So that is b of y. So what is b of y by 2? It is a by root 2 minus y. Right? Okay. So we have everything. We just have to evaluate this integral to find the plastic moment capacity. So MP is nothing but integral y goes from minus a by root 2 to a by root 2. Z goes from minus b of y by 2 to plus b of y by 2. And what is minus b of y by 2? It is minus of a by root 2 minus y2 plus a by root 2 minus y. And what is the integrate? It is y fy dz dy. Note that these are all fy is a constant. This is function of y only. So you can directly substitute the limits for z. It is nothing but minus a by root 2 to a by root 2. So if you can directly integrate z, you get z upper limit minus lower limit, which is a by root 2 minus y minus of minus a by root 2 minus y. So it is 2y fy a by root 2 minus y dy. So this is a simple polynomial. You can integrate directly. And 2 and fy you can take commonly out. It is 2 fy commonly out. Integral. So a by root 2y minus y square dy. dy goes from minus a by root 2 to a by root 2. Therefore, it is 2 fy a by root 2 y square by 2 minus y cube by 3 within the limits minus a by root 2 to a by root 2. Let us evaluate the limits. We just have to substitute into this place. Doing that, you get MP is equal to 2 fy, right? What did we get? 2 fy. So a by root 2 will get a by root 2. Square of a by root 2 is a by 2. So this will become a square by 4 multiplied by a square by 4 minus a by root 2 cube by 3. So a by root 2 cube is a cube by 2 root 2 and 2 root 2 multiplied by 3 will be 6 root 2 minus a cube by 6 root 2. So take things commonly out, you get root 2 fy a cube into 1 by 4 minus 1 by 6, which is nothing but root 2 fy. Sorry, so you need to subtract again, you have this minus term, so this will be so this will contribute to another let me go back. So here what I can do is this this function is valid only in the upper half. For the lower half, it is exactly symmetric about this line. So instead of this integration from minus a by root 2 to a by root 2, I can replace it as 2 times. So just to avoid substituting the lower limits, I can make it 2 times that, right? Because these two are identical about the center line. So you can integrate from here to here and add it up with the moment generated by this. Both are in the same direction, so you can add them up. So otherwise, what you have to do is you have to find b of y by 2, another function in the lower half, and then split the integral into 2 and add them up. But you know that the contribution from the lower half is the same as what is coming from the upper half. So in all the cases, you can make the lower limit 0 and multiply by 2. So you have into 2, 0. This becomes a 4, 0. So we get MP is equal to 4 times Fy by root 2, right? Fy by root 2. So 1 by 4 minus so you get a 1 by 4 minus 1 by 6, which is a cube by 4 minus a cube by 6. This is equal to 4 Fy by root 2 a cube by 12. So you can evaluate what it is. So 4 into 250 MPa, so 250 into 10 power 6 into a cube is a is given as 100 mm, so it is 0.1 meter by root 2 into 12. So evaluate this, you get 4 into 250 into 10 power 6 into 0.1 the whole cube divided by root 2 by 12. So the answer we get is 58.92 kilonewton meters. So we have got MP. Is there any doubt? Is it clear? You can unmute and talk, no problem. Okay, thank you. So we have got MP. So we know option B is wrong and option D is wrong. We got MP as 58.9 kilonewton meters. The next step is to determine the shape factor. What is shape factor? Shape factor S is defined as the ratio of the plastic moment capacity to the yield moment of the beam. I already defined what is the plastic moment capacity. Plastic moment capacity is when the entire section has become plastic. Yield moment capacity is the moment resisted by the section when the extreme fibers of the beam has just yielded. So in the second case, we are going to determine My. How do we determine My? Same procedure. You just have to do the integral, but in this case, sigma will be what? What is usually given by the linear distribution, right? So sigma is a function of y. And what it is, if you take at a distance y, at this distance y, these are similar triangles. So y by, say this is a by root 2. These are similar triangles. So y by a by root 2 is nothing but the stress here is sigma by Fy. So this will give you what sigma is. The only difference is you need to do the integration for the case sigma is equal to Fy multiplied by y by a by root 2. Let us do it. Just so My is equal to same thing. Let us multiply by 2 because this is a line of symmetry. The contribution from top will be the same as that from the bottom. What are the limits for y? Y goes from minus to plus, but we have multiplied by 2, so it is 0 to a by root 2. What are the limits for z? Z goes from minus of a by root 2 minus y to a by root 2 minus y. And what is the moment? Y multiplied by sigma. But what is sigma? Sigma is Fy into y by a by root 2 multiplied by dz dy. Again, there is nothing else is a function of z. All these are independent of z. So you can directly substitute the limits for z. So you get it is 4 Fy integral 0 to a by root 2. I'm taking this minus this is 2 times this. So I'm taking the 2 outside. So I get y square, that's a y here, it's a y here, into a by root 2 minus y dy. Just evaluate this integral, you get 4 Fy. This one is a by root 2, y cube by 3 minus y power 4 by 4. 0 to a by root 2. So what is the value here? So it is 4 Fy. I substitute this here, we'll get root 2 cube is 2 root 2. 2 root 2 into 3 is 6 root 2. 6 root 2 into 2 is 12. So we get a cube by 12 minus. So again, a by root 2 power 4 is a power 4 by 4. And there's already a 4 in the denominator. You get, so there is an a. So a power 4 by 16. So this is a 4, 12, 16. This becomes a 3. This becomes a 4. So it is nothing but Fy by Fy a power 4 by just a minute. There is this a by root 2 outside. So we have this a by root 2 outside. A by root 2 by 12. So what is the answer? You get square root of 2 Fy a cube. And what did we get in the previous case? We got 4 times Fy a cube by 12, which is nothing but 2 root 2 times Fy a cube by 12. So comparing this is MP This is My. You see that MP by My differ just by the factor 2. This 2 is only extra. So MP by My is equal to 2. That is exactly the shape factor. So the shape factor of this beam is 2. So the correct answer is option A. So we are past the time. So I think it is, yeah, I thought we could get into partial differential equations today, but it is too late. We can take it up in the next class. So there are any doubts, please unmute and you can ask me now. You can post in this group, Google group. So as usual, I'll be uploading the presentation, the solution, and the link to the YouTube video in this group. So you can access it there. The link to this Google group I have already posted in the Q&A box. So any other doubts? If you have any doubts, you can ask. Right. This is the link. You can click and join the group. You can also suggest. So what the next session, let us take up partial differential equations. But if you have a problem with other topics of structural engineering, civil engineering, please feel free to post it there. I will take it up in the next class. And if there are any issues with today's session or the previous recordings also, you can post it there. You can message. You can also ask in the next class. You can also ask now. So any doubts? Okay, thank you. I can wait for a few more minutes. If you have any doubts, you can stay back. You can ask. If not, you can also log out. I'll stop the recording. And could any of you unmute and yeah, thank you. So seems like there are no doubts. Let me stop the recording. Thank you all for attending.